So today I want to talk about a fun little geometric result which has to do with inscribing a triangle inside of a circle. So let me draw a picture of that. Try to draw a reasonable circle. And when I say inscribing a triangle, what I mean is an equilateral triangle. So a triangle whose side lengths are all the same, S, S, S. There's an equilateral triangle inscribed inside a circle, meaning that the points of the triangle touch the circle. And just for convenience, I'm going to assume that the circle is of radius 1. So a radius 1 circle, and I'm inscribing a triangle inside of it. And my question is, what is the side length of a triangle inscribed inside of a circle? Right? If the circle has radius 1, right, the distance between the center of the circle and any point on the edge, radius 1, then when I inscribe this equilateral triangle, what's the side length of the triangle? And this is just a fun geometric activity, but actually I'll also use this in a future video when I cover a certain probabilistic paradox. It'll be useful to know this value. So how can we figure this out? Well, what we can do is we can take this radial line here from the center of the circle up to this point in the triangle, and we can continue it down to hit the bottom edge of the triangle. And if I do that, of course, I get a right angle here because the symmetry of the situation means that this is a vertical line and this is a horizontal line. So I get a right angle triangle here. So I can look at this right angle triangle. I'm going to copy it down here. Looks something like this. What do I know? It's a right angle triangle. The hypotenuse has length 1 because it's a radial line of the circle. The bottom leg has length 1/2 s because this length is s, that s is what we're trying to find, and this is exactly half of that. And the other unknown value here, I'm going to label it x. It's the distance from the center of the circle to the edge of one of the triangles, one of the edges of the triangle. So I've got a right angle triangle with these side lengths, and so Pythagorean's theorem, which I have another video on, tells me that x squared plus this side squared, which would give me 1/4 s squared, equals 1 squared, which is 1. Now this is going to be useful for us, but so far it's not terribly useful because the value that I want to know, s, is in an equation with another value, x, that I also don't know. If I have two variables in one equation, then I'm sort of stuck. Right? I don't know, I can't solve for one in a numeric value. But I can do something else here. I can look at this picture and say, actually, there's another right angle triangle, this one. So I'll copy that down here. It looks like this. Actually, it's the same right angle that I had before, but it takes this as one of the legs, and this is the hypotenuse. So the hypotenuse is now length s. This bottom leg here, just like before, has length 1/2 s. And this up here, well, the length of this is x plus this length, which of course is 1, because this is one of the radial lines of the circle. So it's 1 plus x. Now again, Pythagorean's theorem gives me, the Pythagorean theorem gives me 1 plus x squared plus this squared, which is 1/4 s squared, equals hypotenuse squared, which is s squared. And if I sort of rearrange, I can subtract 1/4 s from both sides and get 3/4, so 1/4 s squared rather, and get 3/4 s squared on this side. And I can expand this out to get 1 plus 2x plus x squared. So that's just a little bit of algebraic simplification. But the point is, once again, I have an equation that involves both s and x. But I can combine it now with this equation to actually solve for one of the values. So how can I do that? Well, look, I have 3/4 s squared over here. And if I look over here, I can isolate 1/4 s squared is equal to 1 minus x squared, just by moving the x squared over. So 3/4 s squared, according to this equation, is equal to 3 minus 3x squared. So now if I put these two equations together, what I get is 1 plus 2x plus x squared is equal to 3/4 s squared, which is equal to 3 minus 3x squared. And this is an equation that only has one variable in it, just x. So I could solve it. So let me first rearrange. I get 4x squared, moving this over, plus 2x minus 2 equals 0. Make my life a bit easier and divide both sides by 2. So I get 2x squared plus x minus 1 equals 0. Now this is a quadratic equation, so I can solve it by applying the quadratic formula. I have another video on the quadratic formula if you want to remind yourself of that. But it tells us that x is equal to negative b, so negative 1, plus or minus the square root of b squared minus 4ac, so that's minus 4 times 2 times negative 1, so that becomes plus 8, divided by 2a, so 2 times 2. So that means that we get minus 1 plus or minus the square root of 9 divided by 4, which gives me two possibilities depending on the plus or the minus. On the one hand, I get x equals negative 1 plus 3 divided by 4, which is half. And on the other hand, I get x equals negative 1 minus 3 divided by 4, which is negative 1. And we can reject this solution because the value here that we're trying to find is x. It's a positive number because it's supposed to be a length. So the negative root, it's technically a root of this equation, but this equation was just a constraint. It told me x has to satisfy this equation. But I know separately that x can't be negative because it's a length. So it must be that x is equal to a half. Now we're almost done. We almost have what we want because we got the value of x. But x was actually my label for this height here. What I really wanted was s. So to find the value for s, I'm going to need some more space. So I get x equals a half. I'll give myself some space up here. X equals 1/2, and that implies, using, say, this equation, that since x squared plus 1/4 s squared equals 1, I get a half squared plus 1/4 s squared equals 1. So a half squared is a quarter, so I get a quarter plus a quarter s squared equals 1. And if I multiply both sides by 4, I get 1 plus s squared equals 4. And that tells me that s squared equals 3. And that tells me that s equals the square root of 3. So we've actually solved our value of s. The side length of an equilateral triangle inscribed inside a unit circle. Unit circle just means a circle that has radius 1, is 1/3. The square root of 3. So that's an interesting fact, and instead of ending the video right here, let me leave you with one more sort of bonus fact that we can get out of this reasoning. We saw not only that s equals the square root of 3, but that x, which is this distance here, equals a half. Now what does that mean? Well, this is the center of the circle. So if I were to continue this line all the way to the end of the circle, then this would be a line of length 1. If this is half, you can see that my illustration wasn't perfect here. If this is half, then this also has to be a half. This is a half, and this is a half. And that means that there's a symmetry. I can draw this line, and it's symmetric with this line. And this line and this line are symmetric. And similarly, these lines. So what I get when I add in the sort of mirror image of these three triangles, I flip them to the outside, and this triangle, I flip to the outside. What I get is a hexagon, also inscribed inside the unit circle. And I can ask myself, what's the side length of the hexagon? And I know by the symmetry that it's equal to this length, which is a radial line of the circle. So the side length of a hexagon inscribed inside of a unit circle is 1. exactly the radius of the circle. And to me, that's pretty cool.